Hello everyone, today we'll be presenting a paper called DreamGaussian, Generative Gaussian Splatting for Efficient 3D Content Creations. This work introduces a novel approach to 3D content creation that promises to dramatically improve the speed of generating high-quality 3D models. Here is today's outline, and we'll start from introduction. Recent studies in 3D content creation have pursued two fundamentally different paradigms. One is inference-only 3D native methods that directly creates 3D structures from scratch. This method has the potential to achieve significantly fast generations, maybe within seconds. However, it requires a large dataset to train, which can be a challenge due to limited availability of 3D datasets. Another one is optimization-based 2D lifting methods, which transform existing 2D data into 3D models. While this method provides an alternative solution to the challenge of limited 3D dataset, this method can be computationally expensive and time-consuming, and also may not always produce results that are detailed or accurate as those created directly using 3D datasets. This is where DreamGaussian introduces a novel approach. DreamGaussian capitalizes on the strength on both paradigms, fast optimization time like in the 3D native methods, and the ability to use the existing 2D data like in optimization-based 2D lifting methods. Taking inspiration from DreamGaussian's the state-of-the-art approach that uses score distillation sampling or SDS to generate 3D models from text prompts, DreamGaussian also adopts SDS for optimizations. The key difference lies in 3D representations. Instead of using neural radiance field or NeRF, DreamGaussian introduces a novel approach by using Gaussian splatting as 3D representations. These two different representations lead to distinct advantages and trade-offs in terms of efficiency and quality. And the author argue that the combinations of occupancy pruning in NeRF and SDS loss is ineffective in generative settings, and state that Gaussian splatting is specifically more suitable for this task. To summarize, the main contribution of this work is novel application of 3D Gaussian splatting in generative setting for 3D content creations. And the author introduced an efficient algorithm for converting 3D Gaussian representation into texture mesh along with a UV space texture refinement stage to enhance the visual quality. And the paper presents comprehensive experiments on both image to 3D and text to 3D tasks, showcasing the potential of this paper applied in a wide range of practical applications. Next, we'll go to related work. In 3D representations, we've got NeRF and 3D.js. And NeRF is a state-of-the-art in the field with volumetric rendering, enabling 3D optimization with only 2D supervisions. However, the optimization is slow, which is not suitable for real-time applications, and NeRF excels in reconstruction settings but not in generative settings. 3D.js is an alternative representation that is known for its speed and quality under similar modeling type as NeRF without relying on spatial pruning. This will try to adapt 3D.js into generative tasks, unlocking its potential for creating new 3D content. Text to 3D generations. Recent studies use 2D diffusion model to achieve this task and use NeRF as 3D representation, which often leads to long optimization time due to expensive computations. Image to 3D generations. As the name suggests, this task is generating 3D models from an image, but this task can also be addressed into a single view 3D reconstruction or novel view synthesis, and text to 3D can also turn into image to 3D by using the image captioning model. And two popular models for image to 3D tasks are 0, 1, 2, 3, which excels in novel view synthesis but suffer from long-time optimization time. And 1, 2, 3, 4, 5 is a multi-view reconstruction model that prioritizes speed over quality. Now we'll dive into methods. Here is the method overview. As illustrated in this diagram, DreamGaussian aims to generate 3D models from text or image prompt, and it is divided into two stages. First stage is generative Gaussian sweating, and the second stage is efficient mass abstraction with UV space texture refinement. We'll talk about the detail one by one. First is generative Gaussian sweating, and the input here can be either text or image. And the diffusion prior here is using the pre-trained diffusion model, and at the very first step, it will initialize the 3D Gaussians in random positions within a sphere looking like this gray sphere over here, and then it will periodically be densified during the optimization process. And at this step, the number of Gaussian sweats will be increased, and adding more detail to the 3D representations looking like this example. And the optimization is guided using the SDS loss. For image to 3D task, the input will be RGB image and the foreground mask. And 0, 1, 2, 3 XL will be the diffusion prior. And the SDS loss is similar to the DreamGaussian, just with different variable. So it's basically compared the rendered image from the 3D Gaussian with the original input image, and the goal is to minimize the difference between them, measured using the predicted noise by the diffusions. And this loss also take the camera pose changes to ensure the consistency in different viewpoints. Next is the additional loss for the image alignment. So the loss is to align the reference image and the input image, and it is the same for the transparency image. And the final loss will be the sum of these two losses. For text to 3D, the input is a single text prompt with stable diffusion as the diffusion prior, and it is also similar to the image to 3D, but focuses more on creating the 3D model that matches the text description rather than image. So it takes the render image from the 3D Gaussians and compare it to the text embedding using clip as for the loss function.
Hi, my name is Ben, and I'm going to continue this presentation. Okay, so after the first stage, and in order to further refine the appearance, the author proposed to extract the mesh from the 3D Gaussians. And here they proposed a rather efficient extraction method, and in order to generate texture and do further refinement on the texture. They do this by first constructing the density field using the Gaussians, and then extracting surface using isosurfacing. The density field is constructed with a grid of sample points with defined density, and then they can use interpolation to do the isosurfacing. The author noted that it would be really inefficient if we have to query the entire Gaussian set for every single sample point. So what they do here is first they split the 3D space into multiple blocks, and for each of these blocks they do Gaussian calling. Basically, if a Gaussian center is outside of the block, it is disregarded. And for the sampling points inside of this block, they only have to consider the remaining Gaussians. This is how they speed up the density field construction. So for each sample then, we can try to calculate the density at that given point using the remaining Gaussians. So given a 3D point x here, this density function would provide a density. In the function, alpha is the opacity of the Gaussian, and xi is the center, and sigma is the covariance, which dictates the scale and rotation of the Gaussian. And so with these functions, we can do isosurfacing, and this is done by using margin cube to extract the mesh from this density field. So now that we have the mesh, we can then try to get a texture in order to do later refinements. So how they do it is they first need to initialize a texture. So they unwrap the texture UV map from the mesh. And then they have several different camera poses to render images of the original 3D Gaussian splatting. So each pixel on these views can then be unprojected to texture coordinates, so they can initialize the color of the texture. Okay, so now with the initialized texture UV map, the refinement process is similar. We have multiple different random views and then calculate losses from these random views in order to make the texture more believable. But before we talk about the loss function, the author mentioned an observation. Here you can see that they try to use the SDS function in this texture refinement stage, the loss function used in the first stage, and produced arguably worse result than the method that they later provided. These kind of weird texture patterns is due to the nature of SDS guidance being ambiguous. And this ambiguous in the original DreamFusion paper is handled by NERV, since NERV is a model and can embed rich 3D information in it. But when it comes to texture, it couldn't really handle the gradient. So instead, the author tried to provide a method utilizing this SD-edit method. So to put it simply, SD-edit is a method that can use a diffusion model to refine unrealistic parts of the image, and in order to generate a refined final image. So here you can see these blocks of colors are the unrefined parts, and given an initial noise and further refinement steps, it can produce a refined image. And the above shows that it basically transfers the image from the unrealistic latent distribution to the refined latent distribution. So instead of using SDS, they would try to use a more direct way, which is for each viewing pose, they generate a refined image using this SD-edit method, and then directly calculate MSE loss from it. Okay, so then we can, this is the entire texture refinement process. So again, given a random view, we use the SD-edit method to generate a refined image, and then we calculate the loss to refine the texture map. So here is the definition of the refined image. Having a multi-step denoising function, f, and taking the coarse image, which is the random view, and a starting noise. This noise is related to the starting time step, and this time step is carefully chosen in order to not have the noise be too large for it to be unsalvageable. And also, it could include a condition, which depends on the mode. It could either be the difference in camera pose or the text prompt. And then we can use this as one of the loss function. The author also mentioned that it also adds the reference view loss using the given input image. Okay, so that about wraps up the methodology of this paper, and now I'm going to present some of the results. So here is a visual appearance comparison to previous image to 3D methods. So here you can see DreamGaussian is able to produce more coherent geometry, and also a very refined front-facing view due to the capability of 3D-GS. And here is a quantitative comparison. There are two metrics. First is clip similarity, proposed by OpenAI, which is a image-to-image similarity. And another is generation time. So compared to inference-only method, they have faster runtime, but their overall clip similarity is worse than DreamGaussian. And comparing to 0, 1, 2, 3, especially with this multi-view method with this star mark, the quality loses a little bit. But in comparison with generation time, DreamGaussian is comparably much faster. And here is some sample for text to 3D generation. Finally, for ablation study, here we focus on the first stage, which is Gaussian refinement. So here are some without some design decisions for the algorithm. Here is Gaussian densification. Here is time-step annealing, which is linearly decreasing time-step size. And the final one is without the reference view loss. So all of them are worse off. The results are worse. And specifically for time annealing, it can help produce more coherent geometry. As you can see here, without annealing, it generate a degenerated model. So finally, for limitations and conclusions, as a single view 3D model generation method, reconstruction method, the back-facing view is arguably worse. It is comparatively blurrier to the front-facing view. Also, it exhibits some common pitfalls, such as multi-faces. As you can see here, this penguin has 2 faces, and baked lighting in the image directly onto the 3D model, which is unnatural. As the final part of our presentation, we would like to showcase our experimentation. So just as a small review, remember that in stage 1, we refined the 3D Gaussians through multiple views, calculating SDS losses. These losses help refine the 3D Gaussian splatting to a refined stage. And in the second stage, we utilize the SD-edit method. So remember that SD-edit method has the capability of refining unrefined parts of the image. So in stage 2, again similar to stage 1, we use, given a single view, we generate the refined view of it and then calculate the MSE loss. Multiple views and multiple iterations would generate our final refined texture of the mesh and the refined final result. So here's our improvement. We think that it is possible to apply the second stage refinement technique to any differentiable renderer, and specifically to the stage 1's refinement. So we show that it indeed improves the quality of the 3D.js. And here we only refine the color and opacity because stage 2's technique is mainly about appearances. So we have low learning rates for positions, rotations, and covariances of the 3D Gaussians. Specifically, we only use 1/10 of the learning rate. So here are some of our result comparisons. So this is stage 1's result. So you can see here, after our refinement, there are less weird color patches and more refined appearances. And this is a stage 2 result. Here we can more clearly see that we eliminated weird color patches. So this is another sample. As you can see here, we also is able to eliminate the weird color patches in stage 1 and have a better result in stage 2. So finally, as an ablation study, we showcase that if we didn't have low learning rates for geometry-related parameters, it would degenerate the final mesh extraction, as you can see here. So this is our presentation. Thank you for listening.